All right, welcome to the video lecture for chapters 20 and 21. We just finished talking about the properties of stars, and we are moving on to the topic of the birth of stars. But before we do that, I want to test you again on this HR diagram stuff. This is pretty important. You're going to see a lot of HR diagrams as we discuss the life and birth and death of stars. And so, got to really make sure that you understand what you're doing when you see one of these things. So here's an HR diagram right here. And let's look at how things are laid out. Horizontal axis, we have a temperature at the top. It increases to the left. We have the spectral classes on the bottom. On the vertical axis, we have the luminosity, and we have absolute magnitude on the left-hand side. Generally, the first thing you want to do on an HR diagram is find the sun. So one of the first questions you could be asked here is, what letter corresponds to the sun? And that letter would be A, right? A, because it has a luminosity of 1. It has a temperature just shy of 6,000 Kelvin. It has a spectral type of G2 and an absolute magnitude of 5. So that tells us where the sun is located, and it also kind of helps us identify where the main sequence is, right? It's a narrow strip of data that goes to the upper left and down to the bottom right. So you can easily see here, this must be the main sequence, and then we can see there's regions above, I and G, those must be the giant stars. Above that, there is another region, B and F, those must be the supergiant stars, and there's a region below, H and K, those are the white dwarfs. All right, so I want to go through a series of questions to identify different objects on the HR diagram here. So let's go through these. What object would be the hottest? That object is C, because it's the furthest to the left. Do you want to talk about which one is the coolest? It would be E. E is the furthest to the right. What object is the brightest? The answer is C, because it's the furthest up on the diagram. So C is not only the hottest, but it is the brightest of all the things that are on here. K looks like it's the faintest. What star is the largest? That would be F. F is the largest. It's the closest to the upper right-hand corner. According to the Stefan-Boltzmann law, an object would be very large if it is relatively cool, but very bright. All right. So, what object has the greatest absolute magnitude? That would be K. K has the greatest absolute magnitude. You can see that on the scale here, but remember how magnitudes work. A large magnitude indicates an object that's faint. So when I say what's the largest absolute magnitude, I'm basically asking you what is the faintest object, and that would be K on here. What object do we know definitively has the lowest mass? That would be E. It's the furthest down the main sequence. Remember that we can say additional things about objects on the main sequence that you really can't say for things that are off the main sequence. So we definitively know that E would have the smallest mass here. We don't know for the other regions exactly what their masses would be, simply based on an HR diagram placement. Okay, so what object on here do we know definitively has the smallest mass? That would also be E, right? So on the main sequence here, as you go down the main sequence, let's talk about it like that, you are looking at objects that are cooler, fainter, lower in mass, longer lifespans, right, and smaller. So when I go up to C here, I can say that is the hottest, brightest for main sequence stars, the most massive, the shortest lifespan, and the one that is the largest. Okay. Which object on here would have a spectral type of G2 Roman numeral 3? That would be I. Okay, to say G2 Roman numeral 3, that would be a star with a similar temperature to the sun, but would be classified as a giant star. All right, so this is something you're most likely will encounter on a future exam, and so you want to make sure that you can study a diagram like this and be able to answer any series of questions that come to you on this. And likely this will be attached to a study guide, like a practice version of this, so you can practice even more. All right, let's get into the birth of stars. So when we think about the birth of stars, now, just to be clear, we're using this word birth, right? And I'm also going to use the word death. We talk about stars as if they have a life to them, right? It's very common to describe the life of a star. So there are birth stages, there's life stages, there are the death stages of a star. And to be really clear about that, when we say that a star has a life, we are referring to its fusion reactions. And that's when a star is alive. Something starts the process of fusion and something ends the process of fusion. So our sun is currently alive. It is midway through its life. There was something that started about 4.5 billion years ago that initiated fusion reactions. Well, it really initiated the collapse of a large amount of matter that formed our solar system and then eventually started fusion inside of our sun. And then in the future, which is 4 to 5 billion years from now, the sun will die because it will stop fusion. And the reason it does that is because it just runs out of fuel. It just doesn't have any more atoms to smash together to create energy. So the question is, have stars always existed? Do they form now? Did they form in the past? Well, what we see through observations, and this was, confirmed, really confirmed in terms of how process works by the Hubble Space Telescope. The answer is that, yeah, stars are forming all the time. Our galaxy is considered to have a moderate star formation rate, and that's a few stars born per year. So we do see evidence of stars forming all the time, and we see evidence of stars dying all the time. So that begs a couple questions. What material is around in the galaxy to make stars? And the second question is, what mechanism must exist for that material to actually form a star? So those are the questions we want to sort of address when we initially get into the topic of the birth of stars. So we're going to tackle the first one, which is, what material makes stars? Well, it turns out that the space that exists between stars is not totally empty. It is filled with what is considered sparse dust and gas. And we call this collectively the interstellar medium. Now, what do I mean when I say dust and gas? The terms dust and gas, so let's talk about gas first. A gas is a collection of simple molecules that contain lighter elements with clear spectral signatures to them. So things like water would be considered part of this gas, and so would ammonia, and even things like hydrogen, helium, methane, carbon dioxide, carbon monoxide. Cyanide is a very simple gas. These are all simple molecules, light elements, easy to spot in spectra. And then there's the dust. And the dust contains generally heavier elements. The molecules that make up dust tend to be much more complicated, don't necessarily have clear spectral signatures to them. They tend to simply dim or block light completely. And this stuff exists all over our galaxy. It's all over the space in between stars. Now, we say sparse, and we really mean sparse. I mean, in terms of Earth standards, the space of space is a vacuum. It's like a few atoms per cubic centimeter. It's quite small, but there are enormous distances between stars. So can be a lot of this stuff if you travel through enough of space. So the interstellar medium is really interesting to us because, one, it is the birthplace of stars. If you have a dense enough region of this, there are places in the galaxy where this stuff can kind of collect and something can then trigger star formation. But another reason, and I want to get to this first before we jump into the topic of the birth of stars, is that we have to look through this stuff in order to see distant stars and galaxies. And so that's going to affect how we see things. And we really have to understand when we look out into space, how the light that we receive is actually altered by the stuff that exists between us and the objects we care about. So here's an example of that. Down in the corner here is an example of a moderately dense interstellar cloud. This is part of the interstellar medium, but it's a region that is, sufficiently dense. It's apparently so dense that it's opaque. I mean, I can't see what's on the other side of this cloud here. Just to be clear, like, this is not a void in space. This is actually a molecular cloud, interstellar cloud that is so dense that it actually blocks light from coming through. So that's obviously a main factor, right? If it's blocking light. Now, the other thing you'll notice here, look very closely around the perimeter of this cloud. You'll notice something special about the stars that are found along the perimeter. They are unusually red. They're unusually red. We don't see as many of those reddish stars as we get further out. We see sort of the normal color of stars, but stars that are on the perimeter of this cloud, they have their light altered, and the light is being filtered by the cloud, and it's an effect that we call interstellar reddening. And this picture that's in the upper right here kind of illustrates what's going on. If we try to look at a star through the interstellar medium, what happens is that light gets filtered. And there is a wavelength dependence on the filtering of light. So bluish light or shorter wavelengths of light tend to be scattered a lot more easily than longer wavelengths of light. It's a similar effect to our atmosphere. It's why our atmosphere is blue, because sunlight is the shorter wavelengths of starlight is more easily scattered. So the blue light gets scattered and we get a blue atmosphere. And that happens in a lot of things, especially with interstellar clouds here. So in this picture, they're showing, us trying to look at a star and a lot of this blue light's being scattered away. Now, there's one thing that's a little inaccurate about this picture that probably should be added to this is they show a lot of blue wavelengths being filtered away and like one gets through. To be fair, they probably should show like one red photon being scattered away, because it's not like the red photon doesn't get scattered. It just happens far less frequently. The bottom line is, though, is that when you're filtering out shorter wavelengths of light, a light source will tend to look more reddish in appearance. And that's something that's really important to understand, because say you look out into space and you're looking at an object and it's been reddened by the interstellar medium. Think about this. What are you going to get wrong about its properties potentially? Right? Think about that for a minute. Well, if the object is it's not just that it's red, it actually will be dimmer too, right? Because you're scattering away some light, you're not going to get the full amount of light. So the object is going to appear fainter than it actually is. So you might actually think it's more distant than it really is. And then if it's more red in appearance, you might think that it's cooler than it actually is. And you might assign an incorrect spectral type to it. So this is something that we have to correct for, especially if we look at things that are rather distant. We need to correct for the interstellar reddening, and it's very predictable, fortunately, in our galaxy, how much of this occurs. So can we do anything about this? I mean, it's kind of a problem. We'd like to see, maybe what's inside this cloud, or we like to know what's on the other side of this cloud. So how do we do something like that? Well, if the logic is that longer wavelengths of light aren't scattered as readily, then let's go even longer then, right? What's past the red wavelengths? Well, that's the infrared. And you see down here, there is a picture of Barnard 68. It's the same region of space, but it's taken with an infrared telescope. So we're capturing the infrared light, and look, we can see through the cloud now. The light is scattered, the infrared light is scattered far less now in the infrared, and not only can we see, through the cloud, but we can see, if there's anything actually located inside of the cloud, so anything inside or anything beyond would be able to be seen. And this is a kind of a common technique you'll see in images where we're looking at a really dense region where maybe star formation has taken place. And, star formation takes place in these thick interstellar clouds, and a lot of times the new stars are kind of cocooned inside of these clouds. We really want to see inside these clouds to see what's going on, and the infrared will help us to do something like that. Another example is We discovered the supermassive black hole at the center of our galaxy because we had infrared telescopes and detectors that were able to peer through a lot of the interstellar medium that exists in the galaxy and see all the way towards the center of the galaxy, where we were able to spot the orbit of stars that are close to the black hole, and that revealed the presence of the black hole. All right, so that's what the effects of interstellar reddening is. It's really two things, right? It's reddening, which changes the color, but the other effect is called extinction, and that's simply blocking light. So in Barnard 68 on the visual wavelength picture, you kind of have both. You have the dimming of light or the complete blockage of light, which is extinction, and then you have the interstellar reddening taking place. All right. Now, so let's get to the birth of stars now. Yeah, this stuff will form new stars if triggered to form new stars, right? And what we like to do is we want to think about the interstellar medium as kind of coming in two parts, and the two parts are closely connected to the birth of stars. So what you saw for like Barnard 68 was a dark nebula, was what we call it. So this is a cold hydrogen cloud. It's primarily made up of hydrogen gas, and it's relatively cold. So cold means less than 100 Kelvin, and cold enough that it's not really producing its own light. There isn't really enough thermal energy to produce its own light. And the density is considered to be kind of moderate, maybe on average 100 atoms per cubic centimeter. And this stuff can be quite large. It could contain anywhere between a few solar masses of material or hundreds of solar masses of material. And that's what Barnard 68 is. Now, when clouds like Barnard 68 transition to something that will form stars, a lot of that nebula will transition into an emission nebula. And this is a region where the hydrogen gas is much hotter. So it's hot enough that it actually starts to produce emission lines. We typically see a color in the nebula. Because it's hotter, it is far less dense than the dark nebula. And when you see a combination of these two types of the interstellar medium together in a picture, you are likely looking at a region that is undergoing a star formation process. So here's an example of that. So in the picture here, we see a lot of dark nebula. So all of the dark cloud that you see here, in fact, in particular in this picture, these are called Bok globules. These are basically parts of the interstellar medium that have been triggered to collapse on themselves, and this will be the birthplace of some new stars. You can see some of these globules are more compact. In fact, some start to look a little circular here. Some start to flatten out. That's actually usually what happens, is these things will flatten out and form a solar system in the process. And then the entire region, as you see, is glowing red. So the glowing red is the emission nebula. And we actually see a lot of very luminous stars in the center here. Those are probably some brand new stars that have popped up. And, as this cloud collapses and fragments into pieces, we will see that these pieces will form stars. And the light from those stars is what's going to give energy to the gas that surrounds the area and turn it into an emission nebula. So this picture is a classic, like, this is star formation taking place here. Dark nebula, emission nebula, some luminous stars clumped together. So we see that's actually happening here. All right, so how does this happen? How does an interstellar cloud somehow get triggered to start initiating star formation? Well, this picture is a really sort of valuable picture to study to understand this process here. So this is a star-forming region. We can see a lot of emission nebula, and the dark nebula is a little bit challenging to see, but kind of near the bottom here and kind of going up and to the right, we see a bunch of dark nebula there. You can typically see the dark nebula. One of the ways you can see it is that the density of stars that you see in those areas are kind of less than other areas that doesn't have the dark nebula. So if there's less stars You're noticing in a particular area of the picture, maybe some of them, the fainter ones, are being blocked by the dark nebula. So anyway, what happened here? Well, there was a star at some point in the past that exploded. And that explosion occurred probably somewhere in this region right here. And when a star explodes, it sends out a shock wave, right? If you live in the Alp Valley, you are familiar with shock waves, sonic booms, basically, right? Jets are flying over and they break the sound barrier and they create this giant pressure wave, right? And what happens is you're just sitting there peacefully in your house, and then all of a sudden you hear this bam. When I first moved to this area, nobody told me about the sonic booms. It was a little scary the first time I experienced it. I didn't know what happened. I thought something crashed outside my house. But that's a pressure wave, right? That's a smack, basically. And it's a push. And that's what's happening here in the stars. The stars exploding. And you got this massive bubble of a shock wave that comes out. And if it hits any nearby interstellar medium, it's going to compress that stuff, right? And that's, in fact, what has happened in this image here. In fact, let me go back real fast. I want to explain one more thing before we get into this. Look at Barnard 68 here. Now, this is an example of a interstellar cloud that is currently content with its existence, in the sense that there are kind of two forces at work here. There is gravity. And gravity really wants to kind of crush this cloud. Gravity wants to shrink the cloud down and bring all the atoms towards the center because, gravity is attractive. And that's what, gravity would like to do to this cloud. But the cloud, while very cold, does have some thermal energy to it. And the thermal energy kind of wants to disperse the cloud, right? The atoms want to kind of go in random directions, and that normally would disperse the cloud. It would just kind of disappear as all the atoms go flying away. Well, Barnard 68 is in a balance, right? Gravity is trying to compress it. Thermal energy is trying to make all the atoms disperse away. So there's generally a balance. And if we were to watch this cloud over the course of a long period of time, millions of years, we would see this cloud kind of over the years just kind of morph into different shapes as it kind of floats through our galaxy. And it will stay that way until a process like this disrupts things. And the shock wave that comes out is something that's going to compress the cloud, kind of push all the atoms closer together, and you're given a little nudge to gravity when you do that. And gravity can then take over and then shrink these things down and cause the star formation process to begin. In fact, that's what's, in this image here. This is actually a composite of 3 images that you see on the right-hand side here. There's a visual wavelength image, and that's usually helpful for spotting dark nebula and a lot of the emission nebula. And then as you get further down, these are infrared images. The one at the bottom is an infrared image that really lets you see through a lot of the dark nebula and all the spots that are luminous here. Those are all spots that will soon form some new stars, right? We're seeing a lot of light already being created in this area. On the right-hand side, we see a depiction of how this takes place. You'll notice that there is like a curvature to this cloud. That curvature, as you can see in the picture here, it kind of gets carved out more. I mean, it initially probably had somewhat of a shape like that. In fact, actually, the starlight from this really massive star that caused the explosion probably started to push things out into this arc here, and then the supernova explodes and then pushes all this stuff down, and all the new stars start popping up out of here. Very common mechanism, actually, and somewhat poetic if you think about it, right? It's the death of a star, and it's given life to, potentially hundreds or thousands of new stars. So that's kind of neat idea. Now, what I explained to you there is not the only way that star formation can get started. The trigger through a supernova explosion is a very common way that this can be done. It's not the only way it can be done. Any mechanism that acts to compress the dark nebula will generally result in some kind of star formation. So here's another example of a slightly different mechanism. This is the Horsehead Nebula, because that looks like a horse's head, which is kind of a good name for this, actually. And it's a pillar. It's a dust pillar. And this is part of the Orion Nebula. In fact, it's the region that is seen below the belt of Orion. And what you can't see in this picture, which is kind of above the image here, is the leftmost star on the belt of Orion. It is a massive star. It is a nasty star. It's an O star. Now, O stars are the hottest, most massive, most luminous stars, and they're kind of bullies. They're bullies in the solar system. Not solar system. They're bullies in the galaxy because their starlight can be 1,000,000 times greater than the sun. And that starlight is so intense that it actually can push on its surroundings. And you actually can see, if you see there's streaks of light in this image here, that's the starlight pushing material away, and the light reflects off the material being pushed away, and it creates these streaks that we see here. And that means it's clearing out a lot of the dark nebula that was here. If you look again, look at the density of stars at the top, look at the density of stars down here, you'll notice a difference because there's a lot of dark nebula down here. And all this this gas is being pushed away by the O star. It's turning into an emission nebula because it's being excited by that starlight, and it's collecting down at the bottom here. And that's a compression, and there are new stars forming in this part of the Orion Nebula. And that's another mechanism. It's not as catastrophic. It's not a death of a star, but it is a massive star with starlight so intense that it actually can provide the push, which is going to be that trigger to induce star formation. So that's another way that it's done. So by the way, this triggered star formation that's here, the kind of the pictures on the right that illustrates this. I'm going to put a link in the description of this video. It links to a simulation that kind of shows how this takes place. So you should definitely check that out. All right, so let's ask some questions here, because we got to try to figure out this whole process, because it starts by this trigger that takes place, and at some point you end up with a star. So we got to explore what's this process that takes place here, right? So I got a question for you initially. As an interstellar cloud contracts via gravity, how do you expect its properties to change? So think about this for a moment. All right, the answer here is A. So, yeah, if this cloud lets gravity, start to compress it, there is going to be an enormous release of energy. These clouds possess an enormous amount of gravitational potential energy, and that gets converted into other forms. Initially, it's going to be kinetic energy as everything starts to fall towards the center. And then through collisions that take place, we're going to see a lot of that kinetic energy be converted into thermal energy as we start to get a more denser object at the center of this cloud. So, yeah, that's going to cause the cloud to get hotter. It's going to appear brighter. And then due to conservation of angular momentum, as the cloud shrinks, it's going to start to rotate. And that rotation is going to flatten it out into a disk, right? So all the above is what's occurring here. Now, okay, so that starts the process, right? But what is the initial source of energy? I guess I just gave you the answer in the last question here. So, so I guess this is more like, were you paying attention 30 seconds ago? All right, so what is the initial energy source of a protostar? Now, protostar is going to be, this part of cloud that's about to collapse down and make a new star. So it's kind of like a fetus in a way. Like protostar is the fetus of the star. All right, the answer here is gravitational potential energy. If you got C, then you paid attention to what I said 30 seconds ago. Thank you very much. All right, but yeah, that's where the energy initially comes from. I sort of like to think about this as like lighting a match. Light a match, that's the initial energy source, and you can apply that to something that can catch something on fire, and then the fire starts to go. So that's kind of like the lighting the match, basically. Let's just go through the other options just to make sure you're clear about why they're wrong. Radiative energy from nearby stars. That was the example of the Horsehead Nebula. That energy is not what makes the star get hotter and brighter and all that stuff. That's just a mechanism to initiate the release of the gravitational potential energy. It's what's doing that push, but it's not the energy that actually makes the object heat up and all that stuff, right? Chemical reactions in the cloud. Chemical reactions are never an important source of energy for stars. It's not very much compared to nuclear energy, and that's option D here, nuclear fusion. Well, nuclear fusion is an energy source for stars. It's not the initial energy source, right? The match is the gravitational potential energy, and then when the star gets dense enough and hot enough, the fusion turns on, and that's what the match was meant to light. So, all right, let's keep track of this on an HR diagram. So how we are going to see the whole process take place is by tracking the change of properties on an HR diagram. All right, so let's figure this out. If we try to imagine what these clouds are like when they initially get triggered into star formation, we would expect to see them on the very bottom right of the HR diagram. In fact, I kind of had to stretch out the HR diagram over here to explore a region that we never really see stars in, because stars never get this kind of cold and faint. But initially, this protostar is going to start off as some very cold, very faint clump of matter. And as gravity starts to compress that down to a smaller shape, we will see it get hotter and get brighter, right? That's the release of the gravitational potential energy. So that continues on for a while. By the way, this process has taken millions of years for most stars, millions of years, right? For our sun, just so you know, I'll talk about this a little bit later in the lecture, the whole process for our sun is about 30 million years, right? So, and that's, you know, for humans, that's long. For stars, that's fast, kind of. It's kind of fast, actually. All right, so, yeah, our object is getting hotter. It's getting brighter. And then something interesting happens here. It reaches a peak in its brightness. And then as it continues to heat up, it gets fainter, actually, which seems really odd. Why would an object get fainter if it continues to heat up? That seems to kind of go against our initial ideas of how energy works. In fact, sometimes you can mistake these objects as for giant stars because they're, you know, pretty bright, but they're not incredibly hot. In fact, that's kind of a clue as to what's going on here, right? So if you think about this, why would an object get fainter if it gets hotter? Well, if you remember the more developed stuff in Boltzmann law, that can happen if the object is sufficiently large. And so what we're seeing here is the reason why the brightness starts to go down is because the object has now taken on this more sort of compact shape to it. It's much smaller in size. And that actually limits the luminosity of the object. A lot of the energy that's being created here is trapped inside of the object. And we're starting to see a balance form inside of this object. Gravity is going to be relentless here. It's not going to ever give up. It's always going to try to crush the star down to a smallest size as it can go. And at some point, the star starts to fight back. And this is the fighting back here. As the star starts to get smaller in size, it's going to start to produce a lot of energy, and it's going to start to be able to push back against gravity. And that's really what we're seeing here. And eventually, two things are going to happen in this process here. At some point, the object is going to get hot enough that the fusion reactions will turn on. And that's going to provide a pretty significant support against gravity. And then eventually a balance is going to be reached, right? It's going to eventually achieve its hydrostatic equilibrium. So gravity will compress things so much that the conditions inside of the star are sufficient to fight back. And at that point, you got really your full-fledged star. That's when we say the star has hit the main sequence, right? There's a video I have linked down here I'll put this in the video description. I recommend that you look at this video. It's a really awesome simulation of what we think is actually occurring inside of these clouds. So, you know, the way I'm talking about this process is like there's a single star being formed here. Well, usually these clouds, the clouds fragment into pieces, and the pieces will form individual stars. And there could be anywhere between a few tens of stars to thousands or tens of thousands of stars that form in these clouds. So the video is really cool. I would definitely check this out because it shows a more realistic picture of what we think is going on inside of these clouds. So definitely check that out. All right, so how can we tell that this has taken place? I mean, we're trying to look for now visual signs of this process taking place. And so after the trigger happens, it enters into the stage that we call a protostar stage, right? The protostellar stage is the active accretion of material in the cloud. So when we say accretion, that simply means gathering up of material. You can kind of think about this like rolling a snowball, down a hill, right? That's the usual depiction of that is as it rolls down the hill, it gathers up more and more snow, and it kind of gets larger in size. That's accretion. That's like a good example of accretion. So, and sometimes for the most massive stars, the accretion process becomes visual. And this picture here, it's not a real picture. It's a depiction of what these objects will typically look like, but they will develop a disk because all the material starts to spin rapidly. Everything gets compressed into a disk. And the vast majority of material is going to spiral onto the center of the disk and form the star. Some of it will actually be shot out in what are called bipolar jets. It's a magnetic mechanism that kind of funnels material out the tops and bottoms of the rotational axis of the disk, and it creates these really high velocity jets. And sometimes we see this. In fact, here's an example of this. This is in what's called the Carina Nebula. And in the tip of this pillar, we see a Herbig-Haro object. Now, you don't typically see the disks of these objects. The disks are not incredibly large disks, and they're usually embedded in the nebula, so it's kind of shrouded by all the dust that's there. But we do see the bipolar jets. So there's something apparently pretty massive in this cloud, shooting things out either side too. And you can even see that there's a little, we call this a bow shock, happening on the end of one of these. Looks like there may be a bow shock up here as well. So it's a pretty high velocity gas that's coming out of here. And this could actually, push on the interstellar medium in this area and can also trigger star formation as well in this. So it's not common we see this, but there are some visual signs of what we call the protostar stage. Here's another example of protostars. Now, this is a really famous example. You've likely seen this picture before. It's one of the most famous Hubble images. They call it the Pillars of Creation, and it's part of a larger nebula called the Eagle Nebula. And for this particular part of the nebula, what we see happening here is we see these pillars of dust. Now, one thing that's a little deceptive when you look at these pictures and you see these pillars, it kind of gives the impression that something is like rising up and out of something. And it's actually the opposite that's taking place here. There is some mechanism, and I honestly don't totally remember what happened in the Eagle Nebula here. I don't know if it was a supernova. It probably was a supernova, but it could have been also a massive star, but it pushed material down. And these pillars were, dense enough that they weren't as easily pushed down as the rest of the surrounding material. So we see these pillars form just because everything else was pushed down. And in the tips of these pillars, there's some really interesting things happening here. So let's zoom in on this, the top, the highest pillar here, right? So this is also protostellar stuff. Now, it's a visual wavelength image. We're not really able to peer into this, but you see these little, what we call antennae features here. Yeah, those are stars emerging out of this nebula. And you see all these streaks of light too. So there are new stars that are forming inside of here, and they're starting to produce their own light. And they're kind of ripping this nebula apart from the inside out. All that starlight's going to kind of push everything away. And then we're going to see the new stars emerge out of this nebula. So that's kind of what's happening here. If we could somehow fast forward in time, like go maybe a few million years into the future, we'll see a transition here. We'll see more and more of this nebula get kind of dispersed. And then this pillar is going to probably look something like this image here. This is another star forming region, and it's a little bit more evolved than the last picture. We actually see the top of the pillar is a bit more dispersed, and we're actually able to see apparently what's inside of it. And we see a lot of really luminous, brand new stars that are forming here. At this point, a lot of the accretion process is kind of done here. In fact, we would typically not refer to these objects anymore as protostars. These have now moved on to a stage that we call pre-main sequence stars. There's another term that we use for this, and it's called a T-Tauri star. So that's another type of, another stage that the stars go through. So when the protostar stage is done, usually a lot of the accretion has already taken place, and the star then emerges out of the nebula that it formed in, and then it actually starts to look like a star in the image. Now, that's what we're seeing here. We're seeing things that look like stars. I mean, they are stars. However, we're not entirely certain that they're main sequence stars, because for them to be main sequence stars, there are some conditions that need to be met. The fusion has to start in these objects, and they have to be done with their collapse, meaning they have now attained a hydrostatic equilibrium inside of it. And once those two conditions are met, then we can take off the pre on the name, and they're just main sequence stars. Okay. Now, this picture on the left here is a nature diagram of what's occurring in this particular nebula here. And the dashed line that you see that's placed above the main sequence is what's called the birth line. And it's sort of a theoretical boundary. You remember that the stars, as they evolve to the main sequence, they kind of come up and then they go down. So they kind of look like giant stars to begin with. So then they kind of occupy a space that's near where the giant stars are, and they kind of make their way down and they hit the main sequence. And we believe that when they cross this birth line, so when their properties change and their position crosses the birth line, it's very likely that the fusion reactions have started here. And as you can see, most of these objects are below the birth line. Now, you'll see two different dots here, right? You see solid dots and open circles. The open circles just mean questionable members of the nebula here, whereas the solid circles are confirmed members. One of the issues we have when we look at these regions of space is that sometimes they're so distant that you can't really do parallax measurements very easily. So sometimes you can't tell if an object is actually in the foreground or the background. There's ways that you can decipher that information, but and it's kind of beyond the scope of our discussion right now. But that's just what the difference is. So it appears, even for just the solid circles, that most objects have crossed birth line. So it seems like most have started fusion reactions. But what they have not done is they're still above the main sequence. Right? Some of the B stars, it looks like they've reached, actually. And that's actually pretty commonplace. Stars with a higher mass, because they have a higher mass, their gravitational energy is much greater, and the process of star formation is faster. So it's actually no surprise that we have a lot of B stars on here that have already reached the main sequence. But stars like A and below, they're still puffed up, so to speak. They're still collapsing. They're still trying to attain that gravitational equilibrium inside of it. So they're not quite main sequence stars yet, but they'll get there soon. And for a region like this, it looks like we have another, I don't know, maybe 10, 15 million years for that to take place in this particular cloud. You also notice, where are the O stars, huh? The O stars, they're not here. Did they not form? Well, they probably did form, and they're dead. O stars do this fast. An O star goes through this process in like maybe 100,000 years. And then the life of an O star is like maybe 1 million, maybe 2 million. So you don't see any O stars here, and you might say, well, guess we didn't form any O stars here. No, they formed, and they're already dead. They're already gone. Wild stuff. In fact, look at this one B star up here. My guess is this one's transitioned into supergiant, and then give it another 1,000,000 to 2,000,000 years, and boom, that one's gone too. All right. So let's keep going though. Now the process at some point does stop, and that process stops again when the fusion starts and when the equilibrium is met. And actually, I just kind of talked a lot about the timelines here for things, but you can see, really want to know everything about the sun. Sun's always a good reference. So this show a one solar mass object. This is how its properties change as it hits the main sequence. And we're looking at a 30 million year from the trigger of the star formation all the way to main sequence life. It's 30 million years, which is not incredibly fast. Sorry, it is incredibly fast, actually, considering the fact that our sun is going to live, after it's born, 9-10 billion years of life. 30 million years is not incredibly long. If you had to think about this in terms of human life, let's just say a human lives for 100 years, this 30 million years might be, I don't know, half of a year or something in terms of how long a star would live for. Yeah, maybe 4 months or something like that. So the incubation period, the fetus is 4 months, and then boom, you're a full-fledged adult person and you live for 100 years. That's kind of similar here. Again, up here, if you look, the O stars and B stars, they do stuff really fast. Under 1 million years for a lot of this to take place. So, now when we talk about this main sequence line, we're always showing this main sequence line on these HR diagrams. That's what's referred to as the ZAMS line. It means zero age main sequence. And that line is specifically the properties that these stars have once they have started their main sequence life. So, so all the points on here are the expected properties once these different periods of times end for these objects. Again, the sun, 30 million years. The longest this process takes is for some of the M stars. It could be upwards of 100 million years. So, but once that time has passed, they hit the main sequence and they have their fusion, they have their equilibrium, and they're going to stay this way. And they're going to spend the rest of their lives just chilling out in space, doing fusion reactions, shining maybe some planets around them, got some people. Hopefully they're nice people. They didn't get Earthlings because we're not that great. But anyway, and that star will just keep going until it runs out of fuel. So our sun, 9 to 10 billion years, it's going to keep doing its fusion reactions. And at that 9 to 10 billion years of life, things start to change. The fuel starts to run out, changes start to happen, and that's all next week. That's the next chapters where we're talking about the death of stars. So, all right, so the next thing we're going to get into for the next part of the video lecture for this week is we're going to look at what stars do in their life. And actually, we're going to look a little bit into extrasolar planets because it's tied to the birth of stars. So that's another thing we're going to do. All right, so see you in the next video.